the 3D visualizations after all these math equations. Okay, so as I mentioned briefly at the beginning of the last, or at the end of the last notebook, so we've at this point got symbolic equations of motion, right? And in this case, we've gotten the M and the F that give us two pieces that make up the first order ordinary differential equations that describe how the motion of the system changes with time. And that's gives the relationships between the forces and the torques acting on the body and the acceleration. So we're going to apply some forces and torques and see what the motion is our goal at this point. It's forward dynamic simulation. So we take these and equations and we want to numerically integrate them because, as you can see, they're sort of big, nasty, nonlinear differential equations. There's no analytic solution in general to problems like this. So we are going to switch to numerics at this point and generate some code so we can do these numerical simulations and see the motion of the object. So if you open up the 707 notebook simulation, we'll start through that process. The first part of the notebook, once again, is just importing the correct solutions. If you didn't get the correct solutions in the last notebooks, that'll put you at a good starting point. We're now going to start bringing in code from NumPy, SciPy, and PyDy. So before, we've only worked basically in SymPy land. That's all symbolic. It's a computer-aided algebra system. At this point, we want to jump over to the numerical things. And NumPy offers us the ND array, so we can store arrays of numbers and do vectorized operations on them. SciPy has a lot of tools to work with those arrays. The one that we're going to use here that Obina showed in the first notebook is the ODInt function, which will numerically integrate ordinary differential equations. And then finally, we're going to bring in some code generation that takes the symbolic form of the equations and it will generate numerical functions that will evaluate fast, and so we can do these simulations. And those come from the package PyDy that we had you install. And as I mentioned in the beginning, if you were using Python 3, it's unlikely that that's going to work. So you would want to switch to 2 if you. It's fairly easy. These guys can help you in Anaconda and maybe Canopy 2 if you need to do that. Does anybody need to do that? Okay, great. And then once again, we're going to show a few more symbolic things. We'll bring in the printing. We're going to make some plots, like in the first notebook. So we'll bring in some plotting functions, and I just set the default figure size to be large, so they won't be tiny in the notebook. Okay, so the basic pieces, we have the equations of motion, and they're made up of all these symbolic functions. There's things that are dependent on time in those functions, and then there's constants. All the constants are the things like the masses and the inertias and the acceleration due to gravity that we defined in the problem. So we want to explicitly say which of those symbols in these equations are constants. So we create a list of those constants. Oh, I'm getting that error now for the printing. So some of you have been getting this error. I'm going to fix it because I don't want to see it. In the init printing function, if you do use LaTeX and force it to only compute the matchjacks and not the PNG rendering, we can get rid of that error. And that's just an outstanding bug that will likely be fixed by the end of this week. So here we have the list of constant symbols that we define. So those are all the things. We have the masses and inertia and distances for each of the bodies and gravity. And now we want to tell them which symbols in those big equations are the time-dependent ones. And we have the angles, the 3 angles, and we have the 3 generalized speeds. So there's 6 states to our system. the coordinates plus the speeds. We just put those in a list. So a little exercise so you guys can do some typing. We also need a list called specified that contains the 3 torque magnitudes that we define. So if you can create that, I'll give you a minute or two. Shouldn't take too long. And this is, and we need to explicitly tell which. So the state, the torques are also time dependent, but they're not the states of the system. They're they're what we call external inputs to the system, and those are the what we're sort of modeling these forces that we generate with our muscles. We can activate multiple muscles and generate torques to make our legs extend and flex. And these are going to be fundamental inputs to the system. So if I apply torque to the model, the model may or may not stand up, and or it may do something odd. So everybody got that? That's a pretty simple one. So you get a list of the specified values. Okay. So at this point, we have the equations of motion. We've got these lists of all the pieces that we need, specifying which variables are which, and we're going to make use of the generate ODE function command. Now, what do we want to generate? If we look at the help docs of ODE int, the first argument of ODE int is a function, and that function is supposed to be a function that takes the current value of the states, in this case the letter y, and I'm looking at the wrong function. Yes, it takes the current value of the states and the current time, and it returns the derivative of the states at that point. Right? So that's the form of the function that we need. It has to give the derivative dy dt and take whatever the current does. Does everybody know what numerical integration is fundamentally doing? Does anybody want me to explain that, this step? You do? Okay, good.
We have time.
Yeah, we're in good shape. Plenty of time for questions, so don't be shy. So if I have a single variable that changes with respect to time, right? Maybe it's this curve. We all know from calculus if we had a closed form solution of this curve, that we could take the integral from t, big, t0 to tf, for example, like that. So if I want to integrate it, I'm basically trying to calculate the area under this curve. And sorry, this is x dot. Right. So we've defined how the states change with respect to time, not exactly what the state is with respect to time. And we're interested in finding x. So x equals the integral from t naught to t final of x dot with respect to time. Right. So if we integrate the x dot curve, we'll get x. So the area under this curve tells me what x is over time. And these are, let's direct this more clearly, x, right, is a function of time. That's where we're at. So we formed these for the system. We have to integrate to get that. If they were nice, easy, simple, if x dot was a very simple equation, you could do an analytical derivative. And some systems have that. So like the classic mass spring damper system, you have a spring, a damper, and a mass, the one coordinate x. There's closed form solutions for this. You probably did that in your equation class or other math classes. In general, as soon as you make things more complex than this, there is no closed form solution. So in a numerical integration routine, there's sort of lots of fancy techniques to make this efficient numerical calculations. But the bottom line is that we start at t0. We're going to discretize the system sometimes, and then you make an approximation, right? So we could say something like this. We know you can calculate the area of a rectangle very easy for this small time step and get an estimate of what that area is. And so we walk through each one, right, and we get some kind of estimate. And you can notice if we make the spacing here go to 0, right, we get the perfect curve. So smaller time steps are better, especially if the curve was to change rapidly, right? You want small time steps to be able to get the integral of that. And ODEInt does that for you. So the command ODEInt basically has some algorithms that you give it an initial state here and time, and you give it this function, which we found. It'll walk through here, compute the area, and make a good estimate there. And that's fundamentally what's going on. Any questions about that? So what you have to provide is the ODEInt. You got to provide the time that you want to integrate over. You have to provide some initial value for the state, and not the because there's a constant of integration associated with this. You have to have an initial value of the x values to get the correct estimate, and then you provide the. So that's what the doc string is telling us right here. So it needs a function y, that's func, and it computes the derivative of y at t naught, whatever time you provide it. So at this time, it gives us the value of that function. If we take the 2 times, we can find the area under the curve. So we need to generate that function from our symbolics. And then we give the initial conditions of y, as I said, and a sequence of time points that you're interested in. And we're also going to make use of this args to pass in the constants in the system. So the masses and the inertias and all those things, we'll make use of that. And it outputs y, it's an array, and it contains the value of x, or in this case, as I drew on the board, the value of the states as they change over time. So the first step is to generate this numeric form of that x dot equation. And what we do here is we pass in the mass matrix, the symbolic mass matrix, the symbolic forcing vector that Gilbert showed you at the end of the last notebook. We tell it what are the constants, the coordinates and the speeds, and then the specified inputs, which are the torques that are acting on the system. And if we call that function, it takes those symbolics and generates a function, and we can see that if I look at the type of it, it is a function. And if I check the doc string of that, it says it evaluates the ordinary differential equation. It takes x, the current state, t, the current time, and then any extra arguments. And if we look here, it tells you what the current state should be, the theta 1, theta 2, theta 3, and then omegas. So we have 6 states. Current time value, and then we have this args, which is a dictionary, and there we supply information about the numerical values of the constants. So these do not change with time, so we only need to specify them at the beginning of the integration at one time when we generate so we can pass in a ND array of shape 12 with all the numerical values of this problem, right? And then specified is, it can be one of 2 things. If the torques, the 3 torques, it's asking for the 3 torques ultimately, in those we can give it a constant value, or we can make them 0, or we can supply a function, right? So say I want to apply a torque to the knee that acts like a sine curve. So we could also pass in a function there to define how the torques change over time. And those are things that we specify. So we get this function, and the next two pieces we need to create the initial conditions. Most of the initial conditions are going to be zeros, and here I'm going to set the first three values of the angles to 2 degrees. So we're going to, instead of the person standing straight up like I am, we're just going to lean them over 2 degrees on each of those angles. So there I just use the slice notation of the NumPy array and fill in radians those 2 degrees. So this is the initial state of the simulation. Any questions up to this point? Yep. Yes. The help for the right-hand side that I'm showing right now? Yes. So it takes your system and generates this, and that doc string is for this problem. Yeah. So if you want to do varying mass problems, that's possible. And I think we don't have good problems that test this. So if you have a good rocket problem, we would love to test it. But in general, right, it may.
We wrote the code that allows for varying mass, but usually that requires you to do additional work to make sure conservation of mass and momentum isn't broken. So it's not just as simple as just having exactly. So that obviously is important. So if you know what you're doing, it's fine. Most people wouldn't think about it.
Yeah, we don't have like a canned solution. Say here's my rocket. I can build that and let it go. But you could build something like that with this. And we've had the guy that wrote the Lagrange's equation thing. He was a rocket guy too. So there's some thought to go in there, but we don't have any really good examples for the varying mass stuff. But if you're interested in that, talk to us. We'd love to make sure that it works with that. Yeah. Okay, so those were the initial states, and now we need to give some numerical values for all those constants that he was just mentioning, the masses, the center of masses. So these, I've got some numerical values here. We have another package that helps generate these for people called Yeadon. If you can click that link and look at it if you want. But basically, we've got realistic numbers for the inertia of a person's lower legs, the inertia of their upper legs, their torso, what their mass is, and the acceleration due to gravity. All these things sort of given realistic numerical values for a human. And we store those. So the next, we've got an exercise at this point. We need to specify some numerical values for the torques that we're going to apply in the system. So if you can create first an array that is entirely equal to 0. We just want to create, we're not going to apply any torques, and we're first going to see what the model does without applying torques. And then if you look at the doc string of the right hand side, we need to pass in that args. So look at the doc string and form the args. And then finally, as Abina showed you at the beginning, create a time vector, right, that spans 10 seconds at 60 hertz. So those are three pieces, the last three pieces that we need to pass into ODE int. I'll give you a few minutes on that. Has anybody got this yet? Yeah? Alright, I'm going to go ahead and show the solution. You can use the numpy zeros function and then the dictionary that the right-hand side function needs is simply one that tells it what the constants, the numerical values of the constants and the specified values. And then finally you can create a time vector multiple ways. Linspace is a nice convenient to give 0 to final time. And in this case I set it as 60 Hertz. So now that we have the args formed, we have initial conditions, and we can see if our right-hand side actually returns something. So I can get numerical values if I provide the initial state. I get the derivatives of the initial state with a single call to the right-hand side. So it looks like that this function works and that ODEInt is ready for it. So we'll use ODEInt. Obina mentioned this little point at the beginning, but you got to make sure this args thing is in a tuple, so you need that extra comma, and then it'll integrate the equations of motion. And we see that we get a 300 time point array for the 6 states of the system. So what does that look like? Well, the first thing that we typically do is take a look at that by plotting it versus time. So here I wrote a little function, just wrote a little code to convert it first to degrees, because they're easier for our minds to think about, and give this and just plot the 3 angles. So what do you guys think about this graph? What is interesting or not interesting about it? Huh? Person fell over. Yeah, so we have not only 90 degrees, but 500,000, over 1,000 degrees. So it's doing more than just falling over. And that's typical. We've created an inverted pendulum, and inverted pendulums are well known to be chaotic if you don't do anything to try to stabilize them. Right? So as an exercise, plot the last 3 states, the speeds. Speeds tell us. Anything more interesting? Or does it just tell us the same thing? Yeah, looking around pretty fast. Okay, so we've simulated the system at this point, and we can tell that it's sort of chaotic and unstable. It's not standing. The person's not standing like we want. So the next notebook, we're going to take that data, and we're going to visualize it with the PyDy 3 visualization tool, and we'll have a little fun exercise, I think, at the end of this that you can play around with the visualization. So just to remind us of the you might need this image again when in the exercise. That up. I think that's right there. So first, once again, we're going to import the solutions from the previous examples to make sure you got the right thing. And now we're going to import some objects here that are going to help us build a visualization. So we're going to want to, we're going to make a fairly simple visualization. We're going to use basic shapes. We're going to use cylinders and spheres. And we're going to attach those to the reference frames and the rigid bodies that we've created so that we can get a more pleasing visualization. So that command there shows that there are basic primitives available, and these are, if you guys are familiar with the 3.js library, that's what we use underneath. So we have sort of a mapping to a lot of the shapes and things in there, and we're going to just use cylinder and sphere in this case. The other thing is we've got a visualization frame and a scene. So the visualization frame is a object that basically marries a shape to a reference frame that we've defined previously. So we have a shape and a reference frame, and then we'll use a visualization frame to combine them. And then the scene is where we're going to shove all the visualization frames in so that we can then visualize this scene. So first we need to create we're going to create spheres for just at each joint. And we're going to create cylinders along the torso, the upper leg, and the lower leg. So this first command, we specify 4 black spheres, and we're going to marry these to points that we've previously defined: the ankle, the knee, the hip, and we're going to create a new point for the head. And then we give them some numerical values for the radius, and you can pass in symbolics to these things too if you have those predefined. But we just picked in meters some radiuses for that. And now the way you use the visualization frame is that we say that we have to provide it 3 things, and that's what this shows. If I pull it up, the docstring of the visualization frame explains that you can pass in sort of a variety of things. In this case, we're going to pass in the ankle point that was previously defined. That was a symbolic object. We're going to pass in this shape that we've just defined here, attach a sphere to that point. And the other thing is that we attach a reference frame to control the orientation of the sphere. So I've just selected inertial reference frame because that sphere, doesn't matter which way you orient it, it always looks like a sphere. So if you wanted the sphere to rotate and you had a texture on it or something, you'd probably want to attach that to a reference frame that's moving like you want. But in this case, it's not necessary. So we create those visualization frames. Now we're going to make a new point for the head. We call it in, and it's just going to be at 2 times the torso COM length. So if you remember, we defined the distance from here to the center of your mass. If we want this to be like actually that's the only point that we have available currently. So we're just going to double that and assume the head is up here at the top. So we create a new point by making a vector along the torso frame's y-axis and just double the length of the distance that we had specified in the original problem. And then we create the visualization frame for that. So all of the shapes sort of have a default origin. And for the cylinders, the default origin is at the geometric center of that cylinder. And if you remember, we defined we have the points that locate the center of masses, but we don't have points that are in the center geometrically from your hip to your knee, for example, for your knee to your ankle. So we're going to create these 3 new points that I just called the lower leg center, upper leg center. These are the geometric center, basically just a point in between the 2 legs that's not the center mass, because we have arbitrary values for the center mass, but we want a point that's actually LL divided by 2, LU divided by 2 here, and DT divided by DT in that case. So that's all these next few lines are. We create 3 new points that are going to be locations we can attach the geometric center of the cylinders to on the legs. and you specify those like we've done before with vectors. And here's so we had the constants, symbolic constants, and the numerical values. Let's create a little dictionary there. That'll be helpful when setting up these lengths of the rate of the cylinders. So each cylinder, we're going to just specify a default radius, but the length needs to be the value, the numerical value that matches this dimensions of the person we created already. So I just pass in for the length of the cylinder as the lower leg length, and I use this dictionary to sort of simplify that. And we create a visualization frame with the lower leg frame, the lower leg center point, and the lower leg shape, which is that cylinder. So this marries that cylinder to the center point between the ankle and the knee, and it has a radius that's sort of similar to a human size for visualization purposes, and it also is going to rotate, that cylinder is going to rotate with the lower leg frame. So those are the pieces of the puzzle there, and we do the same thing for the upper leg and the torso. The only difference in the torso is that I do 2 times the torso center mass length, because we never defined like a distance from here to here. Is that clear about visualization frames and how shapes and they relate to reference frames? Any questions on that? Nope. Okay, so the last piece of the puzzle for the visualization is the scene. So the scene, if you look at the docstring, it needs an inertial reference frame or a base reference frame, sort of like the global coordinate systems of the scene. And it needs a base point, right? And we're going to use the origin that we originally did, or the ankle point, because the ankle's not moving in the global reference frame. And then finally you pass it in as many visualization frames as you want. And there's other fun things in there too. We have you can attach the camera to a reference frame, like if you had a vehicle moving and you want to have the camera following it. There's some other stuff like that. So it has some other keyword arguments. You can pass in different things to that. But we're going to have a very fixed camera that watches this scene unfold. So the first thing we can do here is, I didn't follow the docstring exactly in this example, but you can also just supply the attribute visualization frames directly. So here I say the inertial frame is our base global frame, and then the ankle is the base point. And then I give it the list of all those visualization frames we created. And then we have a scene.generate visualization JSON, and it takes a few things. The first thing it takes is the symbolic values of the coordinates and speeds, the states. It takes the symbolic values of the constants. It takes the y was our solution to the the integration, numerical integration, and it takes the numerical constants. And with all those pieces, it's able to generate all the data needed to make these shapes move throughout space. So we run that. And then finally, we run scene.display. And if everything goes well, and the screen's not that great here, but you'll get a scene in your browser. You can move it around. We've made the colors. The lower leg here is blue, the upper leg is green, and the torso is red, and then the top there is our head. So this is really sort of a simple way to attach some shapes to that. And if you hit play, we can see what happens. Right? So we have no muscle forces, no torques. So the person cannot stand up. So it's not a very realistic, we actually, our legs can't bend and hyperextend too far. Right? So you could go back and think about putting in forces that as the leg that prevented it from hyperextending, and then maybe it would fall more like you would imagine a human. You could also add forces that when it hits the ground, it wouldn't penetrate the ground. Those are a little more complex things, but not too awful hard to add. So this simulation just gives you an idea. So now we can see that we formulated a model that has some kind of characteristics. It at least has the same inertial characteristics. We have these pin joints at the legs and the knees. And by the end of the summer too, we're going to have we'll be able to import CAD models to this, so you'll be able to put a human or whatever you're working with. And it's also not gonna it's going to be more responsive than you're seeing on this low res screen. And it'll run inside of a notebook cell. So this is going to have a major upgrade pretty soon. So any questions on this, on the visualization process? Yes? The zooming it, I just used my mouse wheel, or you can do double fingers on your trackpad, and then you can click and hold to rotate it, and I think you can, I'm using my left mouse button to pan. So this is a, I guess we probably don't have great documentation on that, but it's using the 3.js rendering, and it's using sort of some standard trackball motion things to interact with the scene. But yeah, good question, which I should have already repeated. Anything else on that? So who thinks we can make this stand up? You do? You do? Okay, good. Because that's what we're going to try to do in the last notebook. So we have these. This it's not necessarily that much harder.
They're both pretty trivial.
Yeah. Let's see.
I think for a arbitrary number of links, you can stabilize a series of links with a cart movement.
So here's the cart problem you just asked about, and this shows you how to do that. Very classic problem, except it's usually just maybe one or two links. But this is a balancing the 5 link and moving the cart, right? And so you can read that's online. You can find that, and it's linked in a lot of the PyDi materials and stuff too. But we're controlling it a little different, right? We're going to apply torques. Like we don't, as humans, don't actually apply torques, right? We activate muscles. But they all can be resolved to torques about the joints ultimately. So you can do a pretty good approximation of sort of what's happening in a human by saying we can have control over the torques that a person applies about their joints. And like Obina and I both work on walking studies. So we drive walking models and have these simulations that can walk and stuff with the same kind of thing. So hit shutdown server. We'll close that and go back to the notebooks. And so we'll go through the final notebook here. We've got an hour left. I don't think this is not going to take the whole hour. So we'll have a good time for a question and answer, and if you guys want us to demonstrate any other things at the end, I think we'll be able to do that. And so this one's going to be a little math heavy too. Control theory. So we've just given you like a rapid rundown of advanced dynamics, and hopefully haven't overwhelmed you too much. But there's a whole nother realm, control systems and control design, and there's lots of fun things to learn about that. But we're going to use sort of one.
Who here has done controller design?
Okay, we've got a few. Good. There's a lot of techniques. Most linear systems are easier to control. So we have a nonlinear system that we're going to try to control. So that's a little hard. But we're going to use some techniques some linear techniques to build the controller, and we're going to use this really elegant solution that comes from optimal control theory to sort of instantaneously get us a controller with minimal effort. So it's so I picked that way because it's less. Don't have to explain as much theory, and things, but we'll get a controller that probably will make our person stand. Okay, so once again, bring in the solutions from the previous notebooks. We're going to use some things from NumPy again, so we'll bring those functions in. We're going to plot, and we're also going to go back to SciPy. So the whole computer-aided algebra framework for doing these dynamics problems makes it really nice to linearize your systems, right? So linear models that are, I'll give you the form. So in general, we had these equations. We specified x dot equals some general function of the states called u, or the specified inputs, and time. So that's what we've created and we've simulated so far. These are really nasty, long, nonlinear equations. But if you linearize a system about a operating point or a equilibrium point, which we have, what do you guys think the equilibrium points are for the system we've just created? Straight up and straight down, right? So we have two really nice equilibrium points, and we as humans, we stand around our equilibrium point as much as we can. So we can linearize about in this case, we wanted to stand up, so we're going to linearize about the upright operating point. And once you do that, you'll get a new set of equations, and I technically should use a different variable here, but I'm not, that is often written like this, where x and u are functions of time. This is called the state space form. We have a matrix, right? The x dots are linear in the states and linear in the speeds, instead of these generic things, lots of cosines and nonlinear powers and things. So we're going to try to build this ax equals bu system, and that form of the equations is very nice for doing a lot of linear control methods. So if we create the controller for this linear system, it may in fact be able to control our nonlinear system, right? So we're going to do some of this symbolically, and it's going to be a mix of symbolics and numerics at this point, because we're going to do the linearization process in symbolics and then substitute in numbers to get the numerical values for the A and the B matrices. Okay, so like I said, so actually I should have written this form on the board, but we have that mass matrix that we got in the F. The only difference in this form is that mass inverted the mass matrix isn't all the same from this side. But this is the form we're going to work with in the tutorial. And what we are interested in doing is linearizing that equation to find the linear functions of these equilibrium points. There are perturbations around the equilibrium points, and if we linearize the right-hand side of this, f, we can get this linear equation. And that's what we're going to do first. And it turns out that fa and fb, if we calculate the Jacobian of f, of the vector f, with respect to the states and the specified inputs, we're going to get these equations, or these Jacobian vectors, right? So that calculates the partial derivatives of the states with respect to that. And so this is a little hand waving on the linearization process for our problem. The linearization is sort of a trivially simple linearization, but the software can handle more complex systems that have configuration and velocity constraints and give you the proper linear form too. But we're going to use a shortcut of some sense and just do it manually. So once we get FA and FB, we can invert the mass matrix and multiply them, and then we end up with the first order linear differential equation form of our system about the vertical equilibrium point. Right? So the first thing we want to do is specify the equilibrium point, and that's just all zeros. If we set all the angles to zeros and all the speeds to zero, the model as we defined it is standing straight up. And create a little dictionary to map the speeds and the angles to that equilibrium point, and we'll use that a little later. So, quick exercise, create a parameter dictionary that maps the symbolic constants to the numerical constants. And we have both of those things are defined as lists already, so if you can create a dictionary, just like I did on the above, you can make a little dictionary that maps those. So everybody got that dictionary? Mainly just remembering, what the values were, or what the variable names were. Yeah, I'm getting that error. So we'll ignore that. So we've got a dictionary now that has all the parameters in. So the matrix objects, right? Forcing, for example, forcing vector is a SciPy matrix. Right? And they have a lot of nice methods. One of those methods is Jacobian. So to calculate, as I said, to calculate FA and FB, we need to find the Jacobian of the forcing vector with respect to the coordinates and the speeds, the states, and then also the specified input. So here I can compute the symbolic Jacobian of FA, and I'll just simplify it so we can see it. So this simplifies our equations of motion greatly, and that's the linear form of this FA term, which are the is the forcing vector with respect derivatives with respect to the coordinates and speed. So we have a column for each speed, and for each state, and each row represents the 6 equations that we had. So next, I'll do a little magic here to substitute in the numerical values, because all we're interested in is the numerical values. So the first thing is I used the .subs method, and I provided the dictionary of the parameters, all the constant values, and that substitutes numerical values in for each symbolic constant in FA. And then there might be a simpler way to do this, but I need to ensure that I have a NumPy Indy array, because I think the type of this is still a NumPy matrix. A SciPy matrix. What did I do there? Oh, I'd have to execute this again. Yeah. So we still have a SciPy matrix, but I need a Indy array, and that this line does that, converts it to a NumPy array, and make sure that we have floats. So now I have a matrix here that represents that FA term and the equation with numerical values. So as an exercise, create FB sort of in the same fashion, and that's the derivatives with respect to the torques, all the inputs to the system. Matrix to NumPy. So we can So Aaron, our lead SciPy dev, is reminding me that we have a matrix to numpy function. So if I edit that, I think I'll have to generate it again because I'm overwriting variables. Let's see if we get the same thing. Oh, from where is it at? Top level? No underscores. And then if I oh, it does. There's no D-type flag there. Well, so there may be a cleaner way, but yeah, that gives a D-type object. You need to ensure. I guess you could still just do as array or as type or something like that. Does that work? That would work. That's maybe a little simpler. Say that again. Oh yeah, definitely. Okay, you guys got FB figured out? Is that easy? Anybody? Nobody? So to do that, it's sort of a similar process. Just make sure you take the Jacobian of the forcing vector with respect to the variable, the constants. I'm sorry, not the constants, the specified inputs, and we get that. And that's pretty simple. So then we're going to substitute some numerical values in for the mass matrix here. First, the equilibrium dictionary, and that shows you the linear form of the mass matrix and symbolics, and then also converting that to array by passing in all the numerical values for the masses and constants and such. And then finally, we can compute A for the AX plus BU form by, I'm just going to invert the mass matrix and multiply it times FA, and I get my A matrix. Okay? So you can do that for the B matrix. Okay, that shouldn't take too long. B is not defined. So we get the B matrix also. So now we have the linear form of our equations of motion about this vertical equilibrium point. So the next step, now that we have a linear system that we can work with, we can think about creating a controller for the linear system. And like I said, we're going to use a an elegant solution that was figured out years ago that will make it easy. So, in general, control design sometimes or often takes a lot of magic from the user to get the right numbers to make a controller work. And so the original, if you've heard of PID controllers, proportional integral derivative, people have come up with umpteen different methods to try to pick the numerical values in a PID controller that will make things do what you want it to do. And but they're actually, none of them are foolproof. You don't just say, here's my system, what can give me the controller that will make it work. There's still tuning. You have to tune things, and it takes often an experienced engineer to be really good at getting those things. But in the 50s, I guess, if I have my dates right, optimal control theory came into play. And so if you think about a big optimization problem where you want to, in control, in our case, we want, if the system's hanging down, we want to apply some torques that's going to push it back up. So we want to minimize the difference in the angle from the angle that we want. So if I subtract all the angles from vertical and I calculate the difference in those, I want to minimize, right, that. I want to force the system to go to zero. And so you can formulate this as an optimal control problem. And the first step to checking is to know to figure out if it's controllable or not. And there's a nice theory too that tells you whether a system is controllable. And then from this little controllable function, if you pass it the A and B matrices of your system, it'll tell you true or false whether it's actually controllable. And that just means, sort of in a very abstract way, that if I have all those torques, no matter what state the system is, and I have infinite amount of time, infinite amount of time that I can push those states to where I want them to go. And so our system, this theory that's running, and you can look at the source code for that. It creates a matrix that does some comparisons, but we have a controllable system. So with the 3 torques, we can make the system do whatever we want, is what that's telling us. So now that we know it's controllable, this optimization problem can be used, and we'll use the solution for that. So if you imagine a cost function J here, that basically these 2 quadratic terms sort of say, the first term says I want to make the error in the states minimal. So the error away from the equilibrium point, I want to minimize that. The second term says I want to do that with minimal torques, minimal energy applied into the system, right? And the Q and the R matrices are weighting matrices. So I can say, in the optimal control problem, I can say, why don't you weight? I want to be sure I get up to the equilibrium point very fast. So we're going to weight it heavier to get to the state in the right spot, and weight the torques, the energy less. So it'll use a lot of energy and get you up there really fast. And then you could do vice versa. If I weight the torques more and the error in the states less, then I'll use the very minimal amount of torques to try to get it up, and the system will slowly rise to where it's supposed to be. So the nice thing about this problem is that you can formulate this optimization problem, and the designer only has to pick the Q and the R matrices, how much you want to weight the error in the states, or how much you want to weight the energy consumed in the process. And this, and then we can assume that the controller is a simple feedback controller that's a function of this current error in the current state. And so we have a gain matrix K here, multiplied by the state, negated, and that's going to give us the torques we want to drive the system. So this is a simple feedback state feedback controller, and this gain matrix, which in our case is 3 by 6, right? So there's 18 numbers that we have to pick correctly. You can imagine as a human, if I went through and tried to tweak all these 18 numbers to try to get this thing to stabilize, that's a tricky thing. It's pretty, the space that you have to search around in is well, it's just not something humans are made to do. But computers can. They can find what are the optimal gains following this minimization law that ensure that the error in the states and the energy is minimized. And we can, and there's an elegant solution to this optimal control problem that uses the Riccati equation, algebraic Riccati equation, that can analytically, if we solve that, we can analytically get a solution for K, and the only inputs to that are the R and the Q matrices. Those are sort of tunable parameters. Then you can see that it takes the A matrix and the B matrix, and this S term, which is a function of the gains, the R matrix and the B matrix. Does that make sense, or have I looked that up? It's we don't have time to like explain it in great detail, but the bottom line is that you can form an optimization problem. It will tell you what the gains are for the controller to behave in a certain way, and it's a nice, elegant solution. And turns out that solving the algebraic Riccati equation is a function in SciPy, so we can make use of that. And we have all the other numerical values, so we can try to create a controller that follows this law and use this nice analytical solution. So to do that, we're going to import from SciPy linalg. We're going to bring in solve continuous ARE, which stands for algebraic Riccati equation. And if we look at that, the doc string on that. Are Q and R related? The sizes are related. Well, not really. They're just, it depends on how, one's is a function of how many inputs you have.
So the LQR controller is, like Jason said, it's a automated approach designed in a controller. But in reality, there's a lot of like tuning and tweaking of those Q and R matrices, where you basically have to adjust them and play with the numbers to get the performance you want.
But the difference is that there is still some tuning and tweaking, but you're guaranteed to get a controller that works.
Yes.
It may not be performing the way you want, but with other methods, you're not guaranteed to get a controller that works. Correct. Yeah.
But then you still need to go through the process of evaluating the performance.
Yeah.
Adjusting those matrices.
So right now, we're going to ignore performance, and we're going to go the easy route. So it doesn't really matter what Q and R you choose. You're going to get a controller, and it may or may not be the one you want, but it will control the system. So I was just going to look at the doc string here, and you notice that it takes the A matrix, the B matrix, the Q matrix, and the R matrix. That's all we need to solve the algebraic Riccati equation, and we can compute the gains from that solution, this gain matrix. So we're going to go the easy route here. This is very typical to start with. If you just choose Q and R to be the identity matrix of the proper size, it's a good place to start, right? Just numbers on the diagonal, and then you could tweak those to weight things differently. And there's methods in theory about choosing those and doing the proper weighting, and also how to weight the whole matrix. But we're going to go the easy route, like I said. We solve the continuous ARE. We pass it the numeric A and B matrix, the Q and the R, and then I compute the gain matrix from R, B, and that solution. So now we have a 3 by 6 matrix with all the correct numbers that are going to make are going to control our system, right? So if we go back to, so that's the controller that's going to control the linear system. So we created this new, simpler system based off ours. But we're going to try to make it control the nonlinear system that we created. So if we look back at the docstring for the right-hand side function, for that specified value, remember that you could also pass a function. Previously we just passed an array, we made the torque 0. Now we can pass in a function, and that function must take the current value of the states, and it must output the 3 torques. So if we use our new controller, we can write that function. So that's your exercise. Try to write the function that fits what the docstring specifies there, and that follows this. So we have k, let's see, right? We basically want to implement u equals negative kx in that function. So give that a shot. Oh, you know what? I skipped the whole exercise to create the nose. So I skipped we had an exercise on the visualization. We could go back and do that. We were gonna, for you to try to put a nose on the person, and actually I think that's the most fun exercise. So we'll go back to that, or we'll just explore that at the end of this. And if you get the function, go ahead to the next exercise, which is you should be able to integrate the equations of motion, except that you've now passed in this new function, this controller function, to the ODEINT call. And you can plot the trajectories like we did before, and also run the visualization. So you've done all those pieces. The controller function's the new part, and then you guys can tell me once somebody gets it. Raise your hand, and we'll see what you find. Has anybody got the controlled version going? Yeah? Okay. So I'll go ahead and move through that. And what did you find? Stands up. Yeah, so it needs, if you look at the plot, what is the, well, we can look at the plot. I'll just load it. So that was the function that we got args. We integrate the equations with the new function in place. If we plot the trajectories, we can see that, for example, theta 1's the blue, right? It goes more negative first before it comes back positive. That's the ankle angle. So the way we define those were, to look back at the original notebook, I forget the. So we defined everything's about the positive z, so that's all sort of rotating backwards is positive and rotating negative is forward. So for the ankle, it goes back a little and then forward, and the knee angle does the opposite. It goes forward. Did we not switch those? Because it's doing the opposite thing. That am I got my signs right? So it goes. This angle grows and then decreases, and this goes more negative. Both of these two. So yeah, there's you have to do some kind of motion to do that. Say that again. Yeah, so we can watch it. So display that again. And make sure you hit shutdown server when you close these two, because we're having a couple of errors with people. So we start off like that, and we play. You have to bend, looks like you have to bend your knee first more before you straighten back up to have this optimal solution. So that's the sort of comes to the end there. We have a system that we've derived the equations of motion for. We've developed a controller that can make it stand. It has sort of realistic properties of human body's inertia. And we've got about 22 minutes left. The exercise at the end of this notebook, basically says try to explore things. Like you could try to change some of the parameters of the system, see how it behaves differently. You could change the weighting matrices in the controller. And if you look back at the visualization notebook too, which is a couple of fun exercises, maybe you want your visualization to look more normal, or not more normal, but more realistic. So the first one is, can you add a nose to the simulation, on the head sphere. So that's sort of fun to try. Most people like that. And then the other one is maybe you want to add multiple cylinders, so it looks more like maybe a human made out of cylinders instead of just this rod. So we'll leave those two exercises open. You guys can play with them and ask us questions. We'll ask any questions you have. Thank you for your attentiveness throughout the tutorial, and I hope you've learned something, and maybe this stuff will be useful for you in some way. Any general questions or feedback while you guys are playing around with the last exercises? Function, that's correct. Well, inside of that function, it basically says if you pass it an array, just stick the numbers in there. If you pass it a function, evaluate it first and then stick the numbers in there. So it yeah, so the function, well, it has to have specific arguments. It has to have, it has to take the current value of the states and the current value of time, and then it would compute something from that. It has to compute the torques. And so those, inside the OD integration routine, those values are available at every time step. As it steps through that integration, we always have the latest state value, and that gets passed in.
The function name evaluates to the function object, which gets passed in.
Yes.
Sees it as a function object, so
Yes.
how to know what target?
Well, they're just a standard set of arguments. It always has to be the state, the current state, and the current time. That's like it has to be that. Yeah. And those are, and all the constants. If you look at, you can look at the source code. I can show you the source code if you want. Do you want to see the? I don't know if it'll be that clear. It's nothing complicated, too complicated, I don't think. Let's see. Aaron changed. So Aaron here, he tried to change gravity, right? We usually always assume gravity to be 9.81, and he got some different curves. It still was stable. Maybe try. Can you try it with out on the previous one without control and see what happens when you have less gravity? Too. Yeah, the visualization would look. But one thing you found in the visualization, it put the torso off of the knee. And I'm not sure why it would have changed the length of things if you changed G. Something's buggy there. So you guys play with G and see if you get the same weird change in the visualization. If you could do it. Yeah. 3 meters per second. So that if you want to simulate Mars, change 9 to 3, 9.8 to 3. What? Yeah. What's up?
Shut down the visualization server.
Yes.
It says it's okay to close the window.
Yes.
Close the window.
Yes. Okay. Yeah, you might just have to restart the kernel. A couple people got this error, so he's having trouble. If you run a visualization, hit shutdown server, and the server actually doesn't shut down. I think, how did you solve it, Aaron? Aaron, you just. Oh yeah. So there's another method on scene called create static, and our server is actually buggy. So we're rewriting this whole visualization thing as we speak, and these so yeah, don't try to, yeah, if you try to fix it for us today, there's a guy that's sort of working full time on making this app IPython notebook compatible and everything work better. So try restarting your kernel, and then if you want to avoid the server, Scene has a method called create static HTML. If you call that, it'll put a directory in your local directory, in your working directory, that has an index.html, and if you open that, you'll see the visualization, and it won't run a server. It'll sort of avoid that. Yeah, we're not web developers, and we're doing like really bad things on passing JavaScript and stuff back and forth to Python. What's up? Yeah, good question. So that's not something that outputs directly from ODE int. It's only going to provide you the states. I don't have the functionality built in to generate ODE yet, but theoretically you should just be able to pass some other symbolic equations. In this case, you could have functions that give you the torques as a function of the states, which is it's also the gains are part of that for the controller gains, and you can. Yeah. So ideally, right now you could just take the states you have, multiply it by the gain matrix, and you'll get the torques that were used. So that's one easy way to do it, and you can do that. You can always do that. There's always if you have the states of the system and all the constants, you can write some equations that produce whatever other output you would want from the system, right? And ideally we would like to just have that stuff sort of automated too. So you can just sort of specify, well, I want to know how this point moves, what's the x coordinate of that point, or I want to know what is the sum of the torques or something. You know, you can make up any variable. I want to know the kinetic energy of the system through time, and those are all sort of output quantities that are functions of the states, and you can we'll have that sort of seamlessly wrapped in at some point for sure. And if anybody wants to help with that. Yes. Yep. So it's infinitely easier to make controllers in simulation space than real space. So in real life, when you have a real robot, the hardware puts major constraints and things. So those can factor into your Q and R choices too. Yes. Yeah, so you could. Yeah, he's asking if you can augment the plant dynamics or the model that we did with dynamics of controller or actuators, right? So. Yeah. Yeah, I've got a walking model that I'm working with right now where I build a symbolic closed loop system with the controller and the actuators, everything in it. And then you can simulate that closed loop system in the same way. Yeah, so you can, as long as you can write the thing down mathematically, you could do that and make your model more or less closed loop than you want. Yeah, I've got one. It's it's sort of a mess of research code right now, but I can share that with you for sure. Yeah, well, it's on my GitHub repo if you want to look at this, and it's within a few weeks this actually should be working probably. You know, I have there's a repo here called Walking SysID. Oh, I'm sorry. There's also so this gate 2D is a walking model, a planar walking model. And so this has the equations of motion for this derives the equations of motion for a walking model. And then in this other repository I'm working on, this is actually, I guess, I'm working on getting this walking model work, but right now I have that inverted pendulum on a cart problem that generates a closed loop system symbolically somewhere right here. Create the symbolic controller, and then where are the other functions? Well, I don't need to bore everybody with all that, but anyways, there's some repositories here that have some closed loop system simulation stuff where I do things symbolically and things like that. So those are some starts, and if you just email me and you want to, I can point you to that easier. So did anybody try putting a nose on the character? Successful at that? Or play with any other simulation parameters? Tired? Want to call it quits? Well, any last questions? And we can move on to lunch. Yeah, orbital. We've most of the people that worked in this so far, we're like low Earth, own Earth stuff. I don't think we have any good orbital things. Yeah. Are you? Is that what your field is?
More aeronautics.
Yeah.
If you go fast and far.
Yeah, and we don't. It's definitely all classical mechanics. We don't have any.
So, I believe session is adding new cortex system, right, for offerings, accessibility.
Yes.
So, after the summer clear project finishes, reference frames will have multiple different cortex systems attached to them. So that should open up a lot of possibilities for working with those things. Just define an important system, and then attach it to a frame, and then it would just work.
And we're going to have the capability of at least the base pieces in place for having to do some flexible body dynamics, and also the guy that's working on this code is a electrodynamicist and has interest in that. So you can imagine a magnetic field on some body moving in space. So those kind of things, we're close to having some examples and things of that working too. Yeah. So any feedback on the tutorial? Was it too slow, too boring, too fast, too over your head? Anything like that, so we can improve it? Too excellent. All right. Thank you. Well, great. That's great. Thank you. Any other comments? Okay. Okay, good. Okay, well, good. That's good. What about the exercises? Were they fun or boring? Did you learn anything doing that, or should they be augmented?
They don't make you overthink anything. You have to be aware of what's going on.
Okay. Yeah. Okay. Good. No negatives? It's got to be something.
Well, in the context of this SciPy conference, you don't need to go as deep as we would first instruct.
Great. Thanks.
That depends entirely on where.
Yeah. Did anybody find that useful, or was that too? You did? Okay. So we have some people that do, some people don't. Yeah. That's hard to judge. We asked you guys last night whether we should skip that notebook or not because we're at SciPy, and we just decided to throw it in too. Yeah. No, it's good. Good point. Yeah. Okay. Well, if there's no more, thanks again. Oh. Okay.